Hello everyone, my name is Rachel from Imperial College London. I'm very glad to be here to present our work,
Thank you.
Stabilizing peer-to-peer energy trading in prosumer correlation through computational efficient pricing. Power networks are undergoing a fundamental transition with a large-scale deployment of distributed energy resources, including distributed renewable generation, demand, and energy storage resources in distribution networks. This turns traditional passive consumers become prosumers, who can actively manage their consumption, generation, and storage of energy. Under the current electricity market structure in most countries, where small domestic prosumers are served by a retailer who pays prosumers less for excess generation than they charge for energy consumption. In this context, active prosumers owning energy storage units are motivated to self-consume their renewable production. However, if each prosumer independently optimizes its energy storage operation based on its individual demand and renewable generation output profiles, the collective benefits of energy storage flexibility are not maximized. To this end, peer-to-peer energy trading has recently emerged as a new and promising market paradigm, which enables a more beneficial use of prosumers' renewable energy production and energy storage flexibility within a cooperative local energy community. Peer-to-peer trading enables direct and autonomous energy trading between the prosumers. It can offer significant benefits to both prosumers and the distribution network. However, the successful establishment of prosumers' participation in peer-to-peer energy trading faces two key challenges. The first challenge is how to optimally schedule the energy storage units of prosumers. In this work, correlational game is applied as a peer-to-peer trading modeling technique. An energy correlation is formed when a group of prosumers operate their energy storage units cooperatively to minimize the total energy cost of the group. The grand correlation is constructed when all prosumers take part in the peer-to-peer energy trading. Any correlations formed with the absence of any prosumers are called subcorrelations. In this work, we determine the optimal energy storage scheduling of all prosumers by minimizing the total energy cost, namely the correlational energy cost. It is defined as the minimum total energy cost achievable through optimizing the operation of all energy storage units within a correlation, subjecting to their operational constraints. We use value function to quantify the energy cost saving of a correlation, which equals the difference between the sum of the minimum energy cost where each prosumer independently manages the operation of its energy storage unit and individually trade with the retailer at the offered energy prices, and the correlational energy cost of a correlation by collectively optimizing the management of all prosumers' energy storage units. In this work, we investigate the grand correlation, since the value of the grand correlation gives the highest monetary benefit that is accessible to all of the participating prosumers. Having calculated the total amount of monetary benefits available, the next challenge is how to distribute it to each prosumer that adequately maintain their stable participation in peer-to-peer energy trading. We use vector R to represent the benefit distribution. There can be multiple benefit distribution solutions. However, not all of them can guarantee everyone is satisfied in the grand correlation, since some prosumers can achieve higher benefits by forming smaller energy subcorrelations. To measure the dissatisfaction level of an energy correlation with respect to benefit distribution R, we introduce the concept of excess. When the excess of an energy subcorrelation is greater than 0, it indicates the benefit distribution is unstable, and prosumers can break off from the grand correlation and form smaller subcorrelations. Benefit distribution R is stable when excess of all energy correlations are smaller than or equal to 0. To this end, we define core as a set of stable distribution solutions that the total monetary benefit of the grand correlation is completely allocated to each prosumer, and the excess of all energy correlations with respect to benefit distribution is non-positive. In recent years, significant research efforts have been expanded in developing such stable benefit distribution mechanisms and can be broadly divided into two categories. In the first category, total monetary benefit is distributed by identifying a set of local trading prices. These include the mid-market rate and bill-sharing pricing mechanisms. The second category is benefit distribution, including the Shapley value and the nucleolis. However, they either cannot guarantee a stabilizing benefit distribution or characterize great computational complexity. To address these limitations, we propose a computationally efficient mechanism which involves a novel pricing mechanism based on the solution of a single linear programming, and the obtained benefit distribution is in the core. After calculating a complete list of correlation values, the peer-to-peer trading prices and the resultant benefit distribution solution is obtained by solving the following linear programming. The objective function of the proposed algorithm minimizes the largest excess of all correlations by searching through all feasible distribution solutions. The first constraint evaluates the benefit distribution of each prosumer as the difference between its minimum cost when trading with the retailer individually and the minimum cost achievable by trading locally within the grand correlation at the proposed local buy and sell prices. The second constraint ensures the whole amount of monetary benefit of the grand correlation is distributed to all prosumers. The third constraint sets omega as the greatest excess of all subcorrelations, and the last ensures that local buy and sell prices are between the retailer's import and export prices. As such, prosumers are incentivized to remain in the grand correlation irrespective of their trading activities. It can be observed that the solution process of the proposed algorithm relaxes the requirement of computing the unique and lexicographically minimal benefit solution as required in the solution procedure of nucleolis, which in the extreme case needs solving 2 with power of n linear programming problems. On the contrary, the proposed algorithm is more computationally efficient as it only involves the solution of a single linear programming. Then we did several case studies to evaluate the performance of the proposed peer-to-peer energy trading scheme and the pricing mechanism. The performance of the proposed pricing algorithm in financially incentivizing prosumers stay in the grand correlation is evaluated by the axis. As previously introduced, axis identifies the dissatisfaction level of a correlation. When the excess of energy subcorrelation is greater than 0, it indicates the benefit distribution is unstable, and prosumers in this subcorrelation can break off from the grand correlation and form smaller subcorrelations. And the benefit distribution is stable when excess of all energy correlation are smaller than or equal to 0. This table illustrates the greatest excess of the proposed and state-of-art mechanisms as the number of prosumers grows larger. The greatest excess represents the worst-case excess determined over all possible subcorrelations with respect to the benefit distribution solution. As long as the greatest excess is negative, the negativity of excesses of the rest subcorrelations can be implied. Therefore, we analyze only the greatest excess under different mechanisms to study their stability. It can be observed that the nucleolis and the proposed pricing mechanism always guarantee that the greatest excess to be non-positive, regardless of the number of prosumers, suggesting that their benefit distribution schemes are stable and in the core. On the other hand, the greatest excesses are almost all positive under the rest 3 state-of-art mechanisms, demonstrating that the benefit distribution under these mechanisms may not be in the core of the examined prosumer correlational game, and therefore breaking off from the grand correlation to form smaller subcorrelations is always more beneficial for some prosumers. Since only the nucleolis and the proposed pricing mechanism can obtain a stable benefit distribution solution, we then compare their computational performance for an increasing number of prosumers. It can be observed from the following figure that the total computational time for determining the nucleolis increases exponentially with the number of prosumers. This validates the statement we clarified previously, and such massive computational burden largely restricts the adoption of a nucleolis scheme in peer-to-peer trading, despite that it always belongs to the core. Next, we compare the local demand-supply balancing and renewable generation absorption effects associated with the conventional and the proposed peer-to-peer energy trading mechanisms. We examined the 16 prosumer correlational game. The left figure illustrates the net demand or generation of the 16 prosumer correlation, and the right figure illustrates the aggregated energy storage charging and discharging schedules for 3 different cases. The blue curve represents the case without operating any energy storage units for all prosumers. The red curve represents the conventional energy trading structure, where prosumer independently manages the operation of their energy storage units to minimize its own energy cost. And the green one represents the proposed peer-to-peer energy trading structure, where prosumers cooperatively manage the operation of their energy storage units to minimize the total correlational energy cost. It can be observed that, under cooperative energy storage operation, the abundant PV generation during midday period is largely absorbed, stored in energy storage, and is discharged during periods characterized by high electrical demand and none or low PV production. This results in a cooperative energy storage schedule which almost mirrors the net demand profile. The coordinated use of complementary distributed energy resources significantly reduces the peak demand and contributes to a much more locally balanced demand and supply compared to independent energy storage operation. Furthermore, it is evident that, under the proposed benefit distribution and pricing mechanism, prosumers are properly incentivized to share their surplus PV generation directly with their neighbors, establishing successful peer-to-peer energy sharing among prosumers as opposed to independent energy storage operation. In conclusion, we proposed a peer-to-peer trading and pricing mechanism. Under this mechanism, the collaborative operation of prosumers' energy storage units contributes to a more locally balanced demand and supply compared to independent energy storage operation, and enables the excess renewable generation to be efficiently shared within the grand correlation. The proposed pricing algorithm is superior to mid-market rate bill sharing, and they sharply value in financially incentivizing prosumers to stay in the grand correlation, and exhibits a more favorable computational performance than the nuclear OLIs. In the future, we will extend the proposed approach and presented analysis to incorporate flexible demand technologies in the presented prosumer energy model, and develop algorithms to reduce the computation burden of value functions for the computation process of the proposed pricing algorithm. That's all. Thank you for listening. This is my contact detail. If you have further questions, please feel free to email me.
Thank you very much, Rachel. I see 2 questions here. One is from my friend, Professor João Catalao. Great paper and excellent presentation. Congratulations. One question, please. You assume that each prosumer has 50% chance to take the ownership of a PV system or an energy storage unit. What would be the impacts, consequences of considering different chances for each prosumer? Also, have you considered making a sensitivity analysis to address this issue?
Yeah. So in this work, we make this randomly because we assume that not all of the prosumers, they have both PV and energy storage unit, and it is sure that with ownership of different types of those distributed energy resources, it will definitely influence their benefit obtained through attending this peer-to-peer cooperative trading. But in this work, we didn't do any sensitivity analysis on the impact of different of the difference in ownership and their benefit obtained. But it is one of the interesting future aspects we would definitely look into in the future. Thank you.
Thank you. And other, no, I think there are no more questions. So
Okay.
I think there is 2 minutes time for me to pose a question. You define your methodology as addressed to peer-to-peer trade, energy trading. Would there be any difference if it is addressed to local energy markets?
Local energy market. I think the modeling we use is one of the local market. It is one of the model we can apply to the local market. But instead of the previous traditional one, where each prosumer can where each prosumer trade independently with the grid, we propose the kind of a cooperative one, which they can trade energy inside a community first, and after the trading between each other, they can sell the excess generation to the grid as a whole, and or buy the energy deficiency as a whole from the grid. So I think this is the difference, the cooperative and the previous individual market paradigm. Yes.
Thank you. Okay, there is another question, the last one. Thank you for presenting this interesting work. Peer-to-peer energy sharing in radial distribution feeder seems antithetical. Can you comment on the network grid role? Well, this takes over my question, I guess. From Mads Almasalki, right? Good.
Yes, thank you for your question. And I fully understand your concern, because it is also important to consider the physical aspects, for example, the network constraints. However, in this work, in the current work, we did not consider the network in the modeling. Because the focus of this paper is on designing the trading mechanism. So I think it would be also a good promising area for the future extension of the work. And in the future work, we might be able to introduce a coalitional manager who will manage the trading inside the energy coalition, and who will also monitor and control the network related constraints. Yes.
Thank you very much, Rachel.